Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about integrated video systems. Specifically, we're going to do an overview of multimedia traffic design, then we'll talk about video formats, and then finally video design considerations and challenges you may face, but certainly all of this information you'll need to know for your CCDA exam. So let's begin. Video traffic has the same requirements and design consideration as voice traffic. Voice and video applications can be grouped in the multimedia traffic category, and in many cases they should be treated similarly by network devices. This involves ensuring the necessary bandwidth and providing low delay, jitter, and packet loss. Media applications underwent a significant development process regarding IP networks, resulting in many different combinations of audio, video, and data media. Video streams can range from low-definition webcams to high-definition enterprise-level video conferencing systems. As demand for quality video increases, network infrastructure requirements must also increase. Companies might have another source of media streams on their network in the form of unmanaged, not business-critical applications. In response to the explosion of media content and applications, network designers must revise their media application provisioning strategy. Without a properly selected strategy, the network infrastructure might not support all the multimedia traffic that is demanded by users, and the network could easily become congested. Common high-resolution video formats include 720i, 720p, 1080i, and 1080p. The numerical value of the format represents the number of rows in the frame. High-definition video uses a 16:9 aspect ratio, which results in 1,920 columns. The most common video formats and typical bandwidth usages are summarized here. And you would do well to pause the video at this point and study this. Make sure you memorize it for your CCDA exam. Now we reviewed at a high level how video impacts the network, but let's get a little bit more granular so you can understand how it specifically applies to network design. And to do that, we need to get a bit more granular on the technical details of video and what you need to take in account when designing for video. There are three types of video solutions: H323, Cisco Unified Video Advantage, and Cisco Telepresence. With H323, multiple third parties offer H323 video conferencing systems, which can be used to set up a video conference over an IP or ISDN network. The Cisco Unified Video Advantage product uses a PC, video camera, and a Cisco IP phone as a video conferencing station. Now, when a voice call is placed between two users running the Cisco Unified Video Advantage product, a video call can automatically be started with a video appearing on each user's PC. Finally, the Cisco Telepresence. This solution uses CD quality audio and high-definition video displayed on large monitors to create lifelike video conferences. Now, due to the bandwidth-intensive and latency-sensitive nature of video, consider the following when designing or troubleshooting a video network. Like voice, video packets need to be allocated an appropriate amount of bandwidth and treated with high priority. The following are QoS metrics that Cisco recommends for various types of video applications. One-way delay should be between 150 millisecond and 500 milliseconds maximum. Now, please note, for Cisco Telepresence, it should be closer to 150 milliseconds maximum. Cisco Unified Video Advantage can be around 200 milliseconds, and video surveillance can be up to 500 millisecond maximum. Now, regardless for jitter and packet loss, regardless of whether or not it's Cisco Unified Video Advantage, Cisco Telepresence, or video surveillance, all three platforms should be no greater than 10 millisecond maximum with regards to jitter, and 0.05% maximum packet loss. Now, if you're going to design for video, you're going to have to understand the basics of multicast. The complete multicast topic itself is beyond the scope of this video, but certain things you simply will need to know for the exam. And you can count on the fact that you're going to need to understand that there are 3 versions of IGMP. However, only 2 versions are in wide-scale deployment. First is IGMP version 1. When a PC wants to join a multicast group, it sends an IGMP report message to the router, letting the router know that it wants to receive traffic for a specific group. Now, every 60 seconds by default, the router sends an IGMP query message to determine if the PC still wants to belong to the group. There can be up to a 3-minute delay before the time the router realizes that the receiver has left the group. The destination address of this router query is 224.0.0.1, which addresses all IP multicast hosts. Now, there is also IGMP version 2. Version 2 is similar to version 1, except that version 2 can send queries to a specific group, and a leave message is supported. Specifically, a receiver can proactively send a leave message when it no longer wants to participate in a multicast group, allowing the router to prune its interface earlier. In an environment with a version 2 router and a mixture of version 1 and version 2 receivers, the version 1 receivers respond normally to version 1 or version 2. However, a version 2 router must ignore any leave message while version 1 receivers are present, because if the router processed the version 2 leave message, it would send a group-specific query, which would not be correctly interpreted by a version 1 receiver. If you're going to effectively troubleshoot video, you need to understand the concept of distribution trees. To combat the issue of receiving duplicate packets, Cisco routers perform a reverse path forwarding check to determine if a multicast packet is entering a router on the appropriate interface. An RPF check examines the source address of an incoming packet and checks it against the router's unicast routing table to see what interface should be used to get back to the source network. If the incoming multicast packet is using that interface, the RPF check passes and the packet is forwarded. If the multicast packet is coming in on a different interface, the RPF check fails and the packet is discarded. Multicast traffic flows from a source to a destination over a distribution tree, which is a loop-free path. Now, there are 2 types of distribution trees. A source distribution tree. This creates an optimal path between each source router and each last hop router. And then there's a shared distribution tree. This creates a tree from a central rendezvous point, or RP, to all last hop routers. Now, please note, Cisco routers can use the Protocol Independent Multicast Protocol, or PIM, to construct IP multicast distribution trees. PIM's protocol independence means that it can run over any IP network, regardless of the underlying unicast routing protocol. So here's what you've learned. You received an overview of multimedia traffic design. We talked about the unique video formats and then design considerations you need to take into account whether preparing for the CCDA exam or actually designing video for your own network. Good luck in your studies.